welcome back to our thrilling journey into the world of bioinformatics and data analysis. In our previous lecture, we unlocked the power of data visualizations to unveil hidden stories within complex biological data. Today, prepare to embark on an exciting adventure as we delve deep into DNA of plants, hunting for hidden secrets that could save lives. So let's first of all have a recap of previous lectures. So first of all, we did unraveling of biological mysteries by using data visualization. But before we unreveal the thrilling mystery of toxic plants, let's take a moment to revisit the knowledge we gained in the previous lecture. We discovered how data visualization is the key to unrevealing complex biological data, enabling us to uncover hidden truths. We explored the art of plotting, from the elegance of a scatter plot to robustness of histogram and line charts. The matplotlib library was a trusty guide in creating captivating visualization that conveyed critical insight from our data. Always remember, always remember, data visualization is the torch that illuminates the dark corners of data, revealing patterns, anomalies that might otherwise remain concealed. Now brace yourself as we venture into the uncharted territory: DNA sequence comparison, the quest for toxic plants. Yes, my dear friends. So a world. Imagine a world where the plants in your garden could harbor hidden dangers. Yes, you may be blissful tending to your flora, unaware that lurking within the botanical beauty lies a potential deadly secret. This is no science fiction plot. It's a real world challenge that we are going to tackle together. In the world of programming and bioinformatics, BioPython, remember this name, BioPython stands out as a powerful library. It's designed for tasks related to biology and computational biology. BioPython provides various tools and modules that make it easier to work with biological data, including DNA and protein sequences. One essential tool in BioPython is seq object, also known as sequence objects. It's like a Swiss Army knife for biological sequences. You can use it to perform all sort of operations on sequences, such as slicing them, joining them together, or searching for a specific pattern within them. Now let's talk about how this code interact with users. The code begins by asking the user to provide two pieces of information: the DNA sequence of plant and the DNA sequence of unknown toxic gene. Python's input function is used here to collect these sequences as text entered by the user. These sequences are then stored in variables. After that, we also have conditional statements. The heart of the code is a conditional statement, a decision making tool in a programming. It uses an if else structure to determine whether the toxic gene sequence is found within the plant DNA sequence. If the toxic gene sequence is detected within the plant's DNA, a warning message is printed advising caution due to the potential toxicity. If the toxic gene sequence is not found, it assures the user that plant should be safe for pets. What we see here is a simple example of bioinformatics in action. Bioinformatics is an exciting interdisciplinary field that combines biology and computer science. It leverages computational tools and techniques to analyze, interpret, manipulate biological data, including DNA and protein sequences. In this code, we'll essentially comparing DNA sequences to determine potential hazards for pets. but bioinformatics can involve much more complex analysis. This code is an application of BioPython and bioinformatics principles. It takes user input of DNA sequences, checks for the presence of toxic gene, and offers guidance on the safety of a particular plant for pets. Based on this analysis, it's a small but practical example of how programming and biology intersect in this modern world. Before we dive into the code, imagine you are getting ready for an adventurous journey into the world of bioinformatics. But wait, you need some special equipment first. To do that, we use the pip install command. It's like ordering essential gear for our adventure. You just open the terminal and type. What you have to type? You have to type exclamation mark pip, pip install biopython. Remember, whenever you are writing pip install biopython, this complete biopython should be in the small cases, as the programming languages are most of the time case sensitive. That is why you need to write biopython in small letters. This command installs the biopython library, which is like a Swiss army knife, as I've already said, of bioinformatics. It has all the cool tools that you'll need to explore DNA and protein sequences. Now, how do we collect DNA samples? Now that you have geared up, you are ready to collect some DNA samples. Imagine you are a detective. Yes, you are a detective, and you have discovered a mysterious plant in your backyard. You want to know if it's potentially dangerous for your beloved pet Fluffy the cat. So you start by asking your computer savvy friend to run this Python code. I'll tell this Python code for you. The code starts with from bio.seq import seq. Now I'll explain this particular code a bit. Remember, whenever you are writing from bio.seq, remember B is always capital. B is capital, because in the programming language we are very interested and lean toward the case sensitivity. If you write this B in a smaller b, you are writing bio, you'll not be able to get the same result as you wanted, and it will throw a lot of errors. Remember, whenever you are writing bio.seq, B should be capital, I should be smaller, O should be smaller, dot, S should be capital, E should be smaller, Q should be smaller. After that, import, complete import is in small letters, S is in capital letter, and EQ. So we are writing from bio.seq import seq. After that, we are going to take a user input from the DNA sequence. How we are going to do it? We are going to name a variable. The name of the variable is plant underscore sequence. You can take any names of your choice. You can write anything that you want. After that, we are writing a function, a Python predefined function, that is input. Remember, the complete input is in small letters. Don't go for capitalizing the first letter of it, and it will not work. After inside input, we are going to write enter the DNA sequence of identified plant. So whosoever has written the DNA sequence, or whosoever have observed the DNA sequence, the person will enter the DNA sequence in the computer logics or computer program or the prompt. Here you are telling your friend to enter the DNA sequence of the plant. It's like taking a leaf from a plant and sending it off to a lab for analysis, but in a digital way, of course. After that, we'll try to identify the enemy gene. Yes. Next, you ask your friend to identify the enemy gene. This gene is likely the villain in a superhero movie. And You want to know if it's lurking in plant's DNA. So you ask this by writing this particular Python code, which will take user input for the toxic gene sequence. Remember, I'll stop here and I'll just make it more clear for you. In the previous code, we tried to take an input which was your plant gene input that you have given. Now, in the second input, I'm trying to ask my friend to enter a known toxic gene sequence. The before one was input for your plant's gene sequence, and now you are inputting the known toxic gene sequence that you are already knowing, or your friend must be already knowing. So your friend inputs the toxic gene sequence which you already know is potentially, now we'll go forward, which you know is potentially harmful for pets. Now, by doing all this, in the end, BioPython will come to a rescue. It's time for the magic of BioPython to convert this DNA sequences into BioPython's SEQ object. Think of it like converting a secret code into a language that you can understand. So, the Python code for this conversion is BioPython SEQ object plant underscore SEQ. Remember, BioPython. Bio, write it in the capital B, P, write it in the capital P, Python. SEQ, capital S, objects. Plant underscore SEQ can be written anything because it's just the name, equals to SEQ. Remember, whenever you're writing SEQ, S should be in the capitals because it is a predefined function. If you are writing S in the smaller letter, it will not work. So inside SEQ, you're writing plant sequence. You are giving a sequence, whatever the plant sequence was there, you are giving this sequence to this particular function SEQ. It may not, you may find it difficult at certain times, but believe me, it's just very simple computer language that we are going through. After that, first of all, we decided what's the plant sequence by giving it the name of a variable named as plant underscore SEQ. After that, we have given another name of the variable which is toxic gene SEQ. The plant SEQ is the plant that you picked up, you extracted its genes, you can see its genes and you plugged in there, and the toxic plant that you already know, you extracted its genes and you are plugging in the DNAs of the genes inside SEQ toxic underscore gene underscore sequence. You can take any name as of you want, but the function SEQ should be with the capital S, otherwise it will not work. Remember, with this SEQ objects, you're all set to go on a DNA treasure hunt. The moment of truth is here. Whenever we are going to find a DNA treasure hunt, you use Python's if else statement. It may, as a biologist, it may sometimes makes you feel what I am doing, but remember and be assured, if else statements are very easy. If else statement to check if the villainous toxic gene sequence is hiding within the innocent plant's DNA. It's like searching for a hidden treasure, isn't it? So now let us go to the Python code for it and we will check if the toxic gene sequence is present in the plant DNA. So what we'll write if, as in general we spoken English, we generally say if this happens, we'll do this. If this happens, we'll do this. Similarly, if toxic genes SEQ, that is toxic gene sequence in plant SEQ. What does this particular line mean? This particular line means that if I'm able to find this toxic gene sequence, which can be anything, which can be A, B, C, D, and your plant gene sequence can be A, B, C, D, if they both of them are matching, you know that this A, B, C, D is a toxic gene sequence and your plant also contains ABCD, that is again a toxic gene sequence, will print warning, this plant contains a potentially toxic gene sequence. If not, else, if not this, what we'll do. If this happens, we'll do this, this. If not this, we'll write else. Remember to put again 2 colons here. If you are not writing those colons, it will throw an error. Sorry, I can't help this, the problem of the programming languages. So else with colons, print this plant does not contain the known toxic gene sequence. That means it should be safe for your pet. So what we have done, first of all, we try to compare your first gene of sequence, which was A, B, C, D. Just for a time being, just imagine a plant here in front of your eyes, and this plant contains a sequence of gene that is A, B, C, D. I have some sequence in my mind which is A, B, C and S. Anything A, B, C and S. I'll try to put it into the program, and the program will read if DNA or its sequence matches with the known toxic sequence. If both of them are matching, that does mean the plant in front of me is a toxic plant. And again, this all example I'm giving you is a very small level example, just to make you understand the ifs and bits of the codes. We don't do this type of very simple codes. We generally have a very huge data sets inside a website. We just extract those data set. We have n number of toxic gene plants. We try to compare each gene plant with this particular plant that is in front of me, if it's matching or not, if there is something that I could add up to it, and something of that kind. So if you find the toxic gene sequence, you warn your friend that the plant might be dangerous for the fluffy cat, and otherwise you reassure them that it's all clear and the plant is probably safe. And there you have it. You have used Python and BioPython to become DNA detective, to become a DNA detective, protecting your furry friend from potential plants villains. Let's dive into another complex use case in a fun and engaging format: the biomedical breakthrough, finding a cure for sniffles. Imagine you're a brilliant scientist on a quest to find a cure for a common cold. You have discovered a new virus, the sniffle virus, though it's not existing in the real time, but you just named it sniffle virus, and you're determined to crack its genetic code to develop a remedy. You decided to use Python to assist you in your quest. First thing that you'll do is setting up of your lab. You need to set up your lab. In this case, that means installing BioPython. As we have already done this installation of BioPython by using the pip install BioPython, I hope you remember this. Your trusty laboratory assistant, the BioPython, will use the same code, pip install BioPython. Now you are ready to start your scientific adventure. I hope you all want to become some amount of time as a scientist in your life. So now we are going to collect some samples. To uncover the secrets of the sniffle virus, you need samples of its genetic material. You instruct your lab assistant, your friendly Python code, to gather DNA sequence from various sniffle virus samples. Code for this particular Python will be from bio.seq, import seq. We have already seen it. Whenever we are writing this particular code, bio.seq, you have to write B in the capitals. I'm repeating this again and again because this is a common mistakes that we generally do, is writing some capital words into the small words into capital, and it will always throw you errors and you'll not able to understand. It's written bio.seq. I have written bio.seq. Why it is throwing an error? Because you have written B in a small, but it's required to write B in the capital. So remember, write B in the capital and the bio.seq, and S in the capital .seq, import seq. After that, we are going to gather DNA sequences of sniffle virus samples. Supposingly, we have 3 samples. Sample 1 will again write a sequence that is seq. Remember, S is in the capital, and suppose the sample 1 is A T C G T A C C A G G C T T A. Just a sample and random demo that we are giving you. Similarly, for sample 2, we have A G T T A A G G C T T A C C T. Again a sample. On the sample 3, we have G C T T A G G T T A C C T A A. So these samples are like tiny codes or the tiny DNA that we have, or we can also call it as tiny pieces of a puzzle, and you are about to put them together to see the big picture. Now, you know that somewhere within this sequences lies the genetic code of the sniffle virus, but it's not as simple as it sounds. The virus can mutate and its genetic code might slightly differ in each sample. You must find the common genetic pattern that defines sniffle virus. Now we'll try to find a common genetic pattern. So we'll write it something like this. We'll write common pattern. You can have any variables instead of common pattern. You can write combined pattern or something of that kind. I have written and I have given it the name common pattern, common underscore pattern. We generally, whenever we are giving name to some variables, remember to give some underscores. You cannot use spaces while giving names to a variables in a coding language. So that is why whenever we are writing something that involves two or more words, we generally give an underscore within it, so that you know that giving this name and we are using spaces underscores in terms of case of space. So we have three samples. What we are trying to do here, sample 1 plus sample 2 plus sample 3. So it will add up all the samples. Supposingly sample 1 contains just an A, sample 2 contains just a B, sample 3 contains just a C. So the common pattern will become A plus B plus C, that is ABC. It will give output as A, B. You concatenate the sequences, create common pattern. This is where BioPython's SEQ object shines. It lets you manipulate data sequences like a master genetist. So now we are trying to hunt for a cure. Common genetic pattern in hand. You are ready to go hunting for the sniffle virus weasel. You have a known antiviral gene sequence that has been effective against similar viruses, and you want to see if it matches the sniffle virus pattern. So for this, again we have a code that I am going to explain you. Known antiviral gene sequence, going to give a variable named as antiviral gene. You can give it any name as your choice, as of your choice, but remember to give the names with underscore if it is containing two words. Remember, it should start with a alphabet and it should not contain any special symbol or something of that kind. After that, it's equal to SEQ, the sequence that we have given. This is a known antiviral gene sequence. And what is that known antiviral gene sequence? Again, a dummy gene sequence we have given: AGGC TTACC TAAGG. Now comes the exciting, the great comparison. For that, again we have a Python code which checks if the antiviral gene matches the sniffle virus pattern. Again, a small code for this. If antiviral gene in common pattern, that does mean, I'll explain this, don't worry, don't freak out. If antiviral gene is in the common pattern, antiviral gene is in the common pattern, will print Eureka, you have find the potential cure for the sniffle. Else will print keep searching, the sniffle virus still hides its secrets. If the antiviral gene matches the sniffle virus pattern, you celebrate the biomedical breakthrough and have the potential cure for the sniffles in your hand. But if not, you know you have more work to do in your quest to conquer the common cold. And there you have it. You are embarked on a scientific journey using Python and BioPython to discover the cure for the common cold. Who knows? Coding could be so heroic and germ fighting could be so exciting. So please remember guys, this all codings and everything that you have seen, it's a very small example just to make you understand the basics of coding related to biotechnology. But in real life scenario, this type of code will not work. Why? Because this is just an if and else statement. In real life, we don't use if else statements. What we use in real life is the large data sets of maybe a antiviral or doses that we want to create. For example, we have recently seen pandemic COVID-19. Who can forget that? Making doses is very complex process, especially a situation like COVID-19. It cannot run on an if and else statement. For this, we have to collect lots of data, lots of trials, stage 1, stage 2, stage 3, stage 4. And finally, after lots of people put in their lots of effort and seamlessly, then only we are able to come up with a very good dose. But this is just a beginning of what we call as programming related to the BioPython, and that is why I have intentionally made it very niche or very beginners level for you all, so that if you are as a biologist, you don't know even ABC of programming, you will be more familiar with the codes, you will be able to do some play with the code a little bit. That is why this all code I have tried to make it user friendly codes. I've tried to make it something which is related to some real life problems, though it will not exactly solve those real life problems. It will try to solve kind of to certain extent. It will create an inclusiveness inside your brains about how you can go and think of solving this real life problems which you can see around yourself in day-to-day life related to biology using the computer science tool, that is of course the programming languages. Before going, again, one more thing that I want to tell you, that it was really an honor for me because I meet less of the biologists out there, but patiently listening to my codings which might look sometimes boring to all of you. I'm honored and I'm glad. I'll try to deliver more and more such contents. In the next upcoming videos, we are going to deal with certain good examples and use cases, certain good diagrams that we generally create by using the BioPython library, and they are going to be very useful for you. So if you've watched this complete tutorial or lecture till this point of time, make sure you also watch the next or the upcoming video that I'm going to have, because that is something that's going to be some real life examples of how a biologist visualizes different things. We'll see some good diagrams which are of advanced level diagram, which might take hard work to be created in a manual process, but the computers, as we say, will make it easier for you to create the same thing with lots of easiness. So with this, I know I'm taking a bit of more your time, but with this I'll just end my word, and thank you so much for watching this complete lecture, and bye, take care.